entities, you must take account of the magnitude and the direction. Class, are you okay? Are we fine? So you can solve it by just considering the magnitude, adding it, and then that's it. No, you must, when you do it this way, it means that you did not take account of the direction. So the best way to go around this is that represent the vectors within the Cartesian plane, indicating the magnitude and then the direction. So my north-south axis, my west-east axis. Then, so this is the north, this is the south, the west, and then the east. Then represent, we are told that velocity of A is due east. So velocity of A would be here with a magnitude of 2 meters per second. And then velocity of south due velocity of B due south, which is, this is VB, with a magnitude of 5 meters per second. But the concept of the usual network, the usual network situation. My first drawing is gone. My first drawing is gone. So all that I'm saying is that for vectors, you cannot just add the magnitudes. You must take note of the directions as well. Okay. So, just as I was saying, let me just give a quick sketch since the first drawing is gone. So the north-south, the west-east. So V of A, 2 meters per second. V of B, 5 meters per second. Okay, meaning that I've represented the vectors on, or the values on the Cartesian plane. Now with the concept of velocity of A with respect to B equal to VA plus minus VB. It means that to find this, I must negate the velocity of B. And negative vectors have the same magnitude as their positives, but their direction is opposite. So this is minus V of B. Then we realign their directions, and obviously, hello, are we there?
Yes, please.
Okay. So V of A, that is 2 meters per second. So after negating V, then the result the relative velocity of A with respect to B will look like the direction of the resultant between VA and negative VB, which will act along the diagonal. Okay, which will act, so this will be the direction of velocity of A with respect to B, similar to how we were determining resultant force for two forces or vectors that are perpendicular to one another. And because V of A is perpendicular to the negative V of B, we can find velocity of A with respect to B to be equal to the square root of the square of V of A squared plus the square of negative negative v of b squared. And this will be equal to 2 squared plus negative 5 squared, which is the same as 5 squared. And you can determine your answer. This is 29. So square root of 29. What is the square root of 29? 5 point what?
5.38.
38 meter per second. So this therefore gives us the relative velocity of A with respect to B. And you can also be asked to find a direction. And that's the angle between the horizontal and the relative velocity direction. So taking tan of alpha, which is the opposite, the opposite is here we are only considering magnitudes, please. So 5 on 2, then you find. So that's it. Now let's connect this to the question I think sent on the platform just I think yesterday or 2 days ago. 2 cars P and Q are moving eastwards and northwards respectively. Okay, so let's quickly sketch. And then since vectors are indicated by magnitude and direction, we indicate the cars, the velocity of the cars on the Cartesian plane. Please, this is just a sketch. So P and Q are moving eastward and northward. So this is east, this is south, this is north and west. We are told that P is moving eastwards. So the car P is here. I'm coming. Let me check if there is. Godfred, I think it's the network. Please, is it a general problem to all that you can't see? Class, is it a general problem?
No, sir.
Godfred, please rejoin for me, okay? And Q is also moving northwards. So this is Q. We are told that if the velocity of P is 4 kilometers per hour, and the velocity of Q is 3. This is 3 kilometers per hour. What is the velocity of Q relative to P? So we are looking for V of Q with respect to P. So this, by formula, this is VQ plus the negative velocity of P, meaning we must negate P and add it to the positive of that. Negating P would be here. So this is minus P. Okay. So it tells us that the relative velocity of Q with respect to P will be along the diagonal here. So this will be V, Q, P. By magnitude, V, Q, P must be equal to the square root of velocity of P, which is minus 4 squared, plus the velocity of Q, which is 3 squared. And this must give us 5 kilometers per hour. Then direction. This is the direction. Alpha. When we take the tangent of alpha, this is 3 on 4. And 3 on 4, this is equal to 0 point. And what is 3 divided by 4? What is the tan inverse of 0.75? Last quick one. Tan inverse of 0.75.
36.8.
So this is 36.8. Okay. But when you look at the answers and look at the direction, it's within northwest. Okay. When you look at the answers, we have 5 kilometers, 36.9 south of east, which is not correct. 36.9 north of east, which is not correct. However, when we subtract what we had from 90, okay, 90 minus 36.8, this will give us 36.9, sorry. This will give us 53.1, okay? And it will be 53.1 north of west, or west of north. And we have that as C. So this must be the correct answer to our problem. Class, is that okay? Hello, class, are you okay?
Yes, please.
So this must be the correct answer. This must be the correct answer. Then concerning the first question, I think it was given to you during the classes. Let me see if I can retrieve it. Please, if you have any question, ask before we continue. Thank you.
So please, the first one, the which subtract 90 minus the 6 to get the angle from north.
Yes, you see, we had 36.9. When you look at the answers, we don't have 36.9, okay, it's north of west or west of north. Meaning that we must subtract this from 90 to get that. Are you okay?
Yes, sir. Sir, please, last week you also gave us like a particular question.
Yes, that's what I'm even looking for. Can somebody send it to me? I'm trying to. Oh, okay. If a cyclist is traveling along a road due east, I think that question, eh?
Yes, sir.
Okay, so let's quickly look at that cyclist question. Now, if a cyclist is traveling along a road due east at 12 kilometers per hour, so a quick sketch. So the cyclist is traveling at a speed of 12 kilometers per hour due east. So this is velocity of the cyclist. 12 kilometers per hour. Okay. And then wind is blowing from southwest, and wind is blowing from southwest, meaning the direction of the wind is here. It directly divides this quadrant into two. And it is blowing from southwest. Okay. Wind is blowing from southwest at 5 kilometers. This is the velocity of the wind at 5 kilometers per hour. When I looked at your answers, what I saw was that a lot of you represented this, that the arrow of the direction of the wind blow, okay, was moving away from the cyclist. But here we are looking at the interaction between the velocity of the cyclist and then the wind. So the direction of the wind must be towards the cyclist. So you can't have the arrow to be pointing downwards like this. No, when you do it this way, it means that the wind direction has no effect on the cyclist, but it is blowing from southwest or west-south towards the direction of the cyclist. So the cyclist is moving due west, due east, any direction due east. Okay, and the direction of the wind is also towards the direction of the cyclist. Please, are you okay? Are we okay?
Yes, sir.
Now, vectors are equal no matter where they are if they have the same magnitude and direction. So we can equally bring this velocity of the wind. We can also direct it here. Instead of us drawing that, okay, we can also represent it here and it will be equal to what we are doing. So long as this direction is from southwest, we haven't erred in directing it this way. Vectors are equal if they have the same magnitude, direction, and they are parallel to one another. So instead of us drawing it here, we can bring it here, and this will also be the same as the velocity of the wind from southwest. Please, are we okay? Then we are told to calculate the velocity, find the velocity of the wind relative to the cyclist. So velocity of the wind, V of wind relative to the cyclist. And this is V of W plus the negative velocity of the cyclist. So it means that to get the relative velocity, we must negate the velocity of the cyclist. We must negate it. So this is minus VC. Minus VC. Okay. Then we must realign their directions. So we draw the equal vector of VW and put it on the head of minus VC. So if we are basically resolving this into a parallelogram. Okay, similar to what we've done before, resolving this into a parallelogram. So this is the equal vector of VW. VW, same magnitude, same direction. This is VW. Okay. Now, we are told that this is 45. And so this will also be angle of 45. Then, after realigning the direction, this will also be 45 degrees because they are corresponding. So if minus VC is in this direction, then the resultant, which represents the velocity of the wind with respect to the cyclist, will be drawn by from here to this point. So this then will be V of W with respect to C. Because from triangle law of vectors, this plus this must be equal to that. Class, are we okay?
Can you go over it again?
So we must, after redrawing it, we must negate the velocity of the cyclist. And originally it is due east. But when we negate,
why?
Godfrey, why? What? I don't get your question.
Why do we have to negate the cyclist?
Hey, dear Godfrey, you are not following. We are looking for the relative velocity of this wind with respect to the cycles. And this is V of W plus negative V of C. So this is the Y. This is the reason why we are negating the velocity of the cyclist. Because we are looking for the relative velocity of the wind with respect to the cycles. Godfred, are you okay?
Yes, sir.
So this is why we are negating it. So after negating the velocity of the cyclist, you must look at the direction. Negative VC is here, positive VW is here. You must realign their direction as we've been doing in vectors. Okay. So I'm just drawing the equal component of VW on minus VC, and this is it. And after doing that, you realize that direction of minus VC, direction of VW, then what appears to be the resultant of VWC would act along north of west here. Okay. Now, we use, when it is like this, you see, VW is not perpendicular to negative VC. The angle is acute. So we must use cosine rule. Cosine rule to find the velocity of W with respect to C. Yes, Saki.
I still don't get why VW and VWC are formed to make a triangle.
It's not a triangle. It must be parallelogram, but one direction, one side of it will do. Godfrey, we've been doing vectors, how to find resultant vectors when the angle is acute, and we are applying the same thing. We are just reapplying whatever we learned. Please listen. So we have Gideon.
So please, why can't the VWC be a straight line or be taken on the north? So we can extend the VWC touch the north.
You listen.
So the VWC will be the
Okay, what do you matter?
the line right there.
I am at it. Let me take you through A. So we have these two velocities. This is VA. This is VB. The angle between them, this is acute theta. And we are asked to find the relative velocity of A with respect to B. It means that this is equal to V of A plus the negative V of B. So by the concept of relative velocity, we must negate the velocity of B. And Godfrey, this is the reason why we are going to negate B. How would I negate B? Negative vectors have the same magnitude as their positive counterparts. Their direction always opposes one another. That is the concept of negative vectors. So in negating B, what I must do is that I just must negate B. So B must have a direction oppositely to VB, which I've drawn on the diagram. So VA is here, and so this must be VB with the same magnitude as the positive. Please, are you okay with this? Gideon, Saki, Giovanni, and Co. Are you okay with what I've done so far?
Yes, sir.
So we are negating B because of this. And negative velocities have the same magnitude as their positive, but their directions is usually opposite to their positive counterpart. Emelda, are you fine? Ella and Co, are you okay? Now,
Yes.
if this had been resultant velocity, assuming this is not relative velocity, but we are looking for the resultant velocity, VE, VB, and the angle between them is theta. To get the direction of the resultant, we must realign their directions, and that is what we've been doing using equal vectors. So I draw a vector which is equal to this, equal to VB, and put it on the head of A. And draw a vector. This is also VB. And draw a vector which is equal to A and put it on the head of B. So that they will form a parallelogram. This is VA. Having done this, when direction of VA, direction of VB, either below or above, you realize that the direction of the resultant will be here. So this becomes the resultant velocity, V resultant. It is the same thing we are applying here too. After negating B, look at the direction of B. Look at the direction of A. They are not following any order. And so we have to make their directions to follow that orderliness. Okay. And this is using the method we've been using, realigning their direction, drawing equal vectors. So I'm going to draw equal vector of VA and put it on the head of minus VB. Equal vectors have the same magnitude and same direction. So this is also VA. And I can also do it for minus VB. Draw equal vector of minus VB and put it on the head of VA. So that they will form the shape parallelogram. So this is also minus VB. Okay. So after doing that, look at the directions. V minus VA, VA. You can clearly see that their resultant is the direction of VAB is coming to this along the diagonal coming here. This will be the direction of. And we can call this as the resultant because we determine this by negating VB. So this is velocity of A with respect to B. Velocity of A with respect to B. This angle is theta, and so this angle is also theta. They correspond. Please, are we okay? Hello, class, are we okay?
Yes, sir.
Yes, please.
So it's basically the same as what we've been doing to determine resultant. But the only thing is that here we are always negating one velocity. We are always negating one velocity because it's about relative velocity. So after realigning the direction, how do I obtain velocity of A with respect to B? The velocity of A with respect to B can be obtained using cosine rule. We use cosine rule for resultants, and we are using the cosine rule for this, for either acute angle or obtuse angle. Therefore, VAB squared. Daisy, mute yourself.
Alex of the King of Ashanti, built by the British, compensate them.
Let me read some of your messages and then continue. Please, if your camera is on, can you please off your camera? Check if your camera is on. Yeah, I think it's off. Okay. So we can find this using cosine rule, which is velocity of A squared plus, when you square negative B, it will still be VB squared minus this, because I'm looking for this and this angle is opposite to VAB, minus 2VA VB cos of the angle theta. That's all. So that's exactly what we must apply to the cyclist and then the wind question. Saki.
So when the resultant is opposite the angle, it becomes negative.
Minus, yes. And it's plus when in the case of if I'm to find the resultant of VAB and positive VB, and I want to use the angle, this angle, I'll make it plus. So that's all. In the question of the cyclist, let's quickly apply this theory. The cyclist was due east, And then the wind was blowing from southwest. So V of wind, V of cyclist. And we were asked to find the velocity of the, please, what was the question? Find the what?
Find
Hey, come on. Find the velocity
Find
of the
of the wind relative to the cycle.
wind relative to the cyclist. So VW plus negative VC. So we must negate the velocity of the cyclist. And it will be here. Minus VC. Realign the direction. So create an equal vector. This is also VW. Okay, this is also minus VC. So VC, VW, VC, you realize that the resultant, the direction of what we are looking for, which looks like the resultant, VWC, would act along here. Therefore, VW, hello,
this minus VC is moving to the west, but the one on top you have made it move to the east.
it's an error. Thank you. It's an error. So this is, yes, thank you. So VWC is equal to, don't forget this is a square of it, so the cosine rule is equal to V of the wind squared plus V of C negative, but when you square it will be positive, minus 2 of VW VC cos of this angle between, this is 45. And this also correspond with this. So this is also 45. Cos 45. And that's it. Please do it and then give me the final answer. Solve it, put your values in, and then tell me the final answer. Yes, what's the final answer? What is the final answer? Anita,
Yes.
what's your final answer?
So please, I got 9.17.
Giovanni, what's your answer?
I got 18.134.
18.
Yes, sir.
The answer is 9 points. Yes, as Anita called, 9.17 kilometer per hour. 9.17 kilometer per hour. Please, how many of you got the same value? If you got that, please raise up your hand. 9.17. Jasmine got it. Mary. Okay. Gerard. So when you put in the values, okay, you have 5 squared. 5 squared plus 12 squared minus 2 times 5 times 12 times the cosine of 45. So 25 plus 144 minus 10 root of 2. Of course, 45 is root 2 on 2. Okay, so this is 169 minus 14 point 41. No, 414. 14.14. And you must get that. So look at it again. All right, another question. Another question under the same concept to try. I want to see how 2 cars A and B move with velocities of 25 kilometers per hour north and 75 kilometers per hour
Please, can you repeat the question?
2 cars A and B move with velocities of 25 kilometers per hour north and 75 kilometers per hour east, respectively. 25 kilometers per hour north and 75 kilometers per hour east, respectively. Find the velocity of B with respect to A. Find the velocity of B with respect to A. Yes, Gideon.
So please, the formula we use to find the velocity of the wind relative to the cyclist. So please, is it supposed to be plus 2VW?
I said minus because what we are looking for is this, and it's opposite to this angle. And in cosine rule, when you are using, if you have this, 2 forces, the angle between them is theta. By equal vectors, this is F1, F2. Okay. And this is also theta, and the angle between this will be 180 minus theta. So this will be the direction of the resultant. Okay. So F, the resultant squared must be equal to, if you are using the angle opposite to the resultant, it's minus F1 squared plus F2 squared minus 2F1 F2 cos of 180 minus theta. If you are using the angle between the forces, it's plus. So 25 kilometer per hour due north and 75 kilometer per hour due east. Find the velocity of B with respect to A. Saki, have you finished?
Oh, sir, I didn't hear the question well.
I hear you. Hey, Gerard, drop it on the page, okay?
Yes, please.
Are we
Are we
through?
through?
Gideon,
It is at 79.04 kilometer per hour.
79.
0.04 kilometer per hour.
Okay. Who else? Who else is true?
Sir,
Uh-huh.
can you work it on the board?
We'll solve it, but let's wait for what others are doing. What you are doing.
So please, I have 79.06
Come,
kilometer per hour.
come again.
I had 79.06 kilometer per hour.
79. 21.
Yes, sir.
What's your answer? Okay, Yasmin, go ahead and give us yours.
I had 79.05 kilometer per hour.
Okay, so 79 seems to be common. So two cars A and B move with velocities 25 and 75. This is due due north and due east respectively. So V of A, this is 25. V of B, 75. So find V of B with respect to A. So V of B with respect to A, this is equal to VB minus or plus minus VA. It means here we must negate the velocity of A. Okay. And the negative velocity of A will be due south. So minus VA. Therefore, when we realign directions, we'll have the resultant, what appears to be the resultant of VBA acting down here. So VBA would act down here. So that VBA squared would be equal to, that's a simple. So 75 squared plus 25 squared. And what is 75 squared plus 25 squared? What is 75 squared? 75 squared is 5,625. Then
Maybe 6,000.
This is 6,250. And the square root of this, what's the square root of this?
9.05
Kilometer per hour. We can also find the direction. The direction, you find this angle theta, alpha. Alpha is opposite. Okay, opposite, which is 25 over 75. Alpha, therefore, will be equal to the tan inverse of this. What's the tan inverse of this ratio? What's the tan inverse of this?
18.4.
18.433.
So 18.4, meaning the direction is an angle of 18.4. Direction of VBA is 18.4 from the east, or 18.4 plus 90, which will be 18.4 plus 90
So it will be 108.4.
from the north. Okay, so that's it. Yes, Gideon.
So please, can you realign them and then use the formula you use?
You see, you can, but when you do that, it will still come back to cosine rule, Pythagoras theorem, because the angle between them is 90.
Yes, so please. Okay.
All right. Another question for the house to try this time around. So this is the this is the nitty-gritties of relative velocity. Fine. There are other applications which we have to actually, but we must continue and then do something else. So I'm giving you another question to try, this time on three forces acting. This is 300 Newton. This is 400 Newton. And then we have a third force, 200 Newton, acting at an angle of 60. This is 200. And it is acting at 60 degrees to the y-axis. The question is that find the magnitude and the angle it makes with the 400 Newton. Find the magnitude. Find the magnitude and the angle it makes with the 400 Newton force. Find the magnitude of the resultant Fatima, please mute yourself. And the angle it makes with the 400 Newton force. Start with. Gideon.
So please, the magnitude of the resultant is 608.27 Newton. And then the angle it makes with the 400 Newton force is 36.9 degrees.
That your magnitude is what?
So please, the magnitude of the resultant,
And the magnitude is
608.27 Newton.
okay. Let others also try. Then we'll see what they also do. Is somebody through apart from Gideon, do we have somebody else who Saki?
So please, the magnitude I got 519.615.
And then the direction.
So please, I'm still on that one.
Don't forget the magnitude, the direction and the angle it makes with the 400 Newton force. So when you are doing it, be very careful. Meaning the angle it makes with the east. Janelle, are you there? Ella. Hey, people are quiet. Okay, Anita, have you finished?
Okay, so I had the resultant to be 878.91 and the angle to be 6 point.
Okay, then let's look at it together. Well, what you are calling for me is not the angle, the values in the book at all. Okay, so sorry. Let's resolve them into components. This is 0, 300. Meaning it has x, it has vertical and no horizontal. This is also 400, 0. Saki.
So please, can I try for the angle?
I don't get you.
The angle I got 9.89.
What I'm saying is that the answers you are giving me is different from what is in the book. So let's solve it together. And then the third force is also 200 sine 60, which is, okay, both of them are negative. And 200 cos 60. Both of them are negative. So minus, or 200 cos 30 and 200 sine 30. Okay, so summation f of x, we have 400 minus sine 60 is root 3 on 2 minus 100 root 3. And summation f of y is equal to 300 also minus 100 because cos 60 is half. This is equal to, please, root 3 times 100. Calculate root 3. Help me determine 100 times root 3. 100 times root 3.
173.20.
I'll say 100 and what?
173.20.
0.20.
Yes, please.
Then this is also 200. So subtract 173 from 400. Imelda, do that for me. Subtract that from 400.
So 226.75.
226.75. So when you redraw this within the Cartesian plane, summation f of x is positive. Summation f of y is also positive. So we have 226.75 and then 200. Therefore, the resultant would act here. And the direction of the magnitude of the resultant will be equal to 226.75 squared plus 200 squared. And this is equal to, what's the final answer? Just give me the very final answer. Just give me the very final answer.
302.35.
302.35 Newton. Yes. And the answer is 302.4. And then the direction. The direction is 41.4. So let's see. If we take tangent of alpha, meaning the angle it makes with the east, which is the axis on which the 400 Newton, we have tan of, this will be 200 over 226.75. Divide and then give me the final answer for
41.41.
exactly 41.41 degrees. So how did you do it? Because nobody called this answer for me.
Please, I thought you meant relative velocity, so I used the way of relative velocity to
The question is even written on the board. Find the magnitude of the resultant and the angle it makes. So what you were not looking at instructions. Giovanni. Anita.
Please, my mistake was that I didn't negate the other vector.
That in the moment you overlook that, you cause your own okay, because you must always, for vectors, you must always take into consideration the quadrants within which the vector is. Please take note of this petty mistakes. Take note of them. All right. Please, is there any question? Asada, is there any question? Okay. The next area, are we ending on Thursday? Yes. Or let me pick your views. Are we ending on Thursday?
No.
When?
Today.
Who told you? Professors, can we end on Thursday?
So please, can you go back? I want to see something.
Because I want us to start Newton's laws of motion. Not so much. At least if we could talk about it, okay, for some time, it will help you.
Okay.
Yes, please.
And I won't bother you with calculations, okay? And work sets. All right, Newton's laws of motion. Please, are you true? I want to move to the next page.
Yes, please.
So Newton's laws of motion. Newton's laws of motion. Class, what is actually responsible for the motion or movement of a body? What causes the movement of a body? Or in physics, we are always saying a particle. What causes motion?
Unbalance.
Pardon? Oh, share your views. What causes motion of a body? Yes, Frank.
Sir, please, a force.
A force. There must be a force. And so okay, somebody was also talking about an unbalanced force. So force is responsible for motion. Yes. Can we have any other view of what is responsible for motion? Yasmin. Yes, Gideon.
That is acceleration.
Acceleration. Okay, so we have force and acceleration. Emelda, are you there? Emelda, oh, she's gone.
Yes, please.
What causes motion in your view? Okay, so way back, scientists were looking at what is actually responsible for the motion of a body. And then the most renowned scientist was Aristotle. So whatever Aristotle says is considered to be, or was considered to be, the final view, because he was the most everything, scientists, philosophers, whatever it is, technologists, So whatever Aristotle says was the final. And so Aristotle's view of motion was that, yes, force is needed for an object or a body to move. But a body would only move when there is a continuous force acting on the body. So it means that for a body to move, example, car to move, the car must be continue to be pushed. So we must continue pushing the car. The moment the force is taking off, the car will stop. So Aristotle came with the view that yes, a continuous force is needed for a body to move. Indirectly saying that when the continuous force is removed, the body comes to a stop. Okay, so now Aristotle's view to some extent actually was true, because when you are pedaling a bicycle, the bicycle will continue to move so long as the paddling thing is being done. When the rider stops pedaling, the bicycle moves for some time and then stops. When the car engine is on, so long as the engine stays on and the driver presses on the accelerator, the car would continue to move. When the engine is off, okay, when the engine is off, the car will move for some time and come to a stop. So the next question is that what causes the stoppage of a body? What causes an object to stop moving or motion? Yes, that's the next question. What causes an object to stop? To stop being in motion? Yes, Gideon.
That is friction.
Friction. Giovanni.
An external force.
An external force. Frank.
An opposing force.
An opposing force. So are we saying that the body does not come to a stop because that force, exerted force, is removed, but rather because the body is being acted by an external force? Because Aristotle is saying that a force is needed to cause an object to move, and for the object to continue to be in motion, the applied force must be applied continuously on the body, meaning that when the applied force is removed, the body comes to a stop. And you are also saying that a body stops not because the applied force is removed, but you are saying because it is stopped because of an external force. Is that your view? Godfred, your hand is up.
Sir, please, the body will stop because the source of the force is removed.
And so that is my question. That was Aristotle's view. Okay, so he was just saying that the body stops because the applied force is removed. Meaning, if I'm pushing you, Gideon, for you to continue being in motion, I must continue to be pushing you. The moment I stop applying the force on you, you stop. Is that what causes an object to stop? Okay, you have given your views. The point is that, yes, an object stops not because the applied force is removed, but truly an object comes to a stop because it is rather opposed by another force. Elikem.
Sorry, it's a mistake.
Okay. So an object stops rather because an external force is acting against it. So when you are riding a bicycle and you stop pedaling, the bicycle will stop not because you have stopped pedaling, but it is because the bicycle is being opposed by frictional force. So yes, those of you who made mention of frictional force, external force, it is true. When a car is moving and the engine is off, the car will move for a while and come to a stop because frictional force is acting against it. If there is no friction, when the engine is off, the car will continue to move continuously. And that is demonstrated by, you see, whenever people are playing on icy ground, on icy ground, friction is minimal. So whenever people are playing on icy floor or ground, and then they push themselves, they would continue to move until they hit something. Okay, that is also demonstrated by whenever you are playing on very smooth, well-tarred floor, and then water is poured on the floor. Whenever you push yourself on the floor, on a tarred floor, you can continue to move until you collide with something. Is that okay? So where frictional force is very minimal, an object would continue to be in motion. This is also demonstrated whenever astronauts are in space and they get to mid-air. In mid-air, air resistance, there's no air, so air resistance is not there. So astronauts, when they get to mid-air, can off the engine of their spacecraft, and the spacecraft by itself would continue to be in motion. They will only on the engine when they want to change direction or increase speed. So in mid-air, where air resistance is not there, it's like frictionless. There's no drag. The body will continue to be in motion. So this is actually what causes an object to stop. Then another scientist by name Galileo also conducted a very simple experiment to add his voice to what Aristotle said. Galileo picked a stone and then, projected or throws the stone. And he realized that, yes, for the stone to move, there must be a force applied on it. But once the force is applied, you don't need the applied force to continue to be exerted on the stone for it to move. Once there is first application of force, the stone will by itself move all along. So based on Galileo's experiment, he came to the realization that yes, a force is needed for a body to move. But once the force is applied, the force shouldn't be continuously be applied on the body to move. But as the body is in motion, and an external force will be needed again to change the speed of the body. So from Galileo's experiments, Galileo came to the conclusion that yes, external force will be needed, or is needed, to change the speed, one. Two, external force will also be needed to change the direction. So change speed, and changing speed has to do with increasing speed or decreasing speed. And the same external force is also needed to change direction. Change direction. So external force, once the body starts being in motion, external force will be needed to change the speed, as in increasing the speed or decreasing it. And the same external force will also be needed to change the direction of a moving body. Is that okay? So this is what Galileo added to what Aristotle said. Then another scientist by name Sir Isaac Newton put Aristotle's view and then Galileo's view together to formulate his laws. Hence, Newton's laws of motion. Newton put together three main laws. Newton's first law of motion, second law of motion, and then the third law of motion. Newton's first law of motion says that a moving body, let's begin with a stationary body. A stationary body will continue. Let me explain before I give you the law itself. A stationary body will continue to be at its state of rest. At its state of rest, will continue to be at its state of rest. Hello, Grace, be here, a stationary body will continue to be at its state of rest, and a moving body will also continue to be in motion with a constant velocity, unless an external force is applied. What Newton is saying is that if you are at rest, you will continue to be at rest. And when you are in motion, you also continue to be in motion with a constant velocity unless an external force acts on you. So a stone, okay, at one position will continue to be there unless somebody pushes it. And if you are also moving, you also continue to be in motion with a constant velocity unless an external force acts on you. And when the external force acts on you, it will either increase or decrease your speed. Please, the second part of Newton's first law of motion, the part which has to do with a body moving with a constant velocity, is applicable to frictionless surfaces. That part is only applicable to frictionless surfaces where there is no, on surfaces where there isn't friction. Okay, so that is Newton's first law of motion. A stationary body will continue to be stationary, and a moving body would continue to be in motion with a constant velocity unless an external force is applied or acts on the body. This is Newton's first law of motion. Please, is there any question? Quick one. We have 5 minutes, so if you have anything to ask, let's hurry up. Newton's second law of motion. Newton's second law of motion. From the first law, Newton is saying that a body would only move when an external force is applied. And whenever an external force is applied, a body would accelerate. If you are stationary, okay, Giovanni, if you are stationary and I push you, when you were stationary, your velocity was seen to be 0. When I push you, your velocity would increase. An increase in your velocity means you are accelerating. So Newton's second law of motion is only saying that a body would only accelerate when an external force is applied. Class, are you there? A body would only accelerate when an external force is applied. A body accelerates. Frank.
So can you say the acceleration of a body is directly proportional to the force applied?
Yes, I'm coming to that. A body accelerates when an external force is applied. And it can also be said to be the acceleration of a body. The acceleration of a body is directly proportional to the applied force. That is why when a car breaks down on the road and Frank is called to assist him, or Frank is called to come and push. As Frank exerts the force, the car can only shake. But when Giovanni, when Gideon, when Isaac, when Imelda, and the rest of you come and add forces, then the car will begin to move. Okay, so you can the movement or the change in the speed or the velocity of the car with respect is the acceleration, and this acceleration is directly proportional to the external force applied. Okay, when it was only Frank, the car could only shake, but when Gideon Isaac, Imelda, Anita, and co came to add force, the car's speed can this time increase. That is acceleration. So the acceleration of the car is directly proportional to the external force applied. Meaning, when the applied force increases, the car's acceleration would also increase. When the applied force decreases, it would also decrease. This is Newton's second law of motion. But we'll state it. It is also stated in a different way. We'll look at that on Thursday. Discuss the third law and applications of the first law, second law, and then the third law. This is where we will draw the curtains on our whole 3 months of online session. So class, let's try as much as possible and then avail ourselves on Thursday. Okay. Is that okay?
Yes, please.
Okay. May the good Lord be with you. Take care of yourselves and bye-bye. If you have any question, do not hesitate to send it to me. All right. Bye-bye to all of you.